Hey everyone, and welcome to our Homework 8 walkthrough. We are getting close to the end of the class. I'm a little sad. We do only have, I think, around 10 lectures left. The last lecture is on May 2nd. So, we've got about a month left for us. And I think there's a couple of holidays in April. So, this might be, we're getting towards the end of the homeworks here as well. I think we've got maybe another homework 9, 10, 11, and 12. We've got another 4 homeworks. So we're definitely at least 2/3 of the way through the class. But anyway, let's get started with homework 8 and the walkthrough that we're going to go through today. So I did intend for homework to be a little bit shorter than other homeworks. I wanted you guys to have time to really think about the problems and the way you approach them. So we'll see how that works out. So the first problem we have here is actually called longest increasing subsequence. So if you guys remember in class, I mean, this should ring a bell. In class, we covered the longest common subsequence. Okay, and you guys probably remember the definition of that. In this problem here today, we're actually going to cover the longest increasing subsequence. So again, it's just a way to make sure that you guys understand the definition of subsequence, understand optimization. Obviously, this is a dynamic programming problem. A lot of the problems this homework are going to be dynamic programming. But anyway, let's jump right in and actually read the description, right? So longest increasing subsequence. A is an array of length n containing real numbers, right? So it could be integers, could be floats, could be whatever. Longest increasing subsequence, which we're going to call LIS, so I don't have to write it every time. So longest increasing subsequence is going to be called LIS. Of A is a sequence, 0, I1, I2. So these are indices. So it's basically saying like you have some indices, I1, I2, I3, dot, 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 IL. So you have L indices, right? Where like L is less than N. So you have some indices in your array, and they're also ordered, right? So I1 is bigger than or less than I2. I1 is less than I2, I2 is less than I3. So that means, the indices are like, take index 0, index 7, index 4, index 7, index 3, index 10, 20, 20. Like this, these are the I1s, I2s onto IL, right? Where L is like another variable. And these values here are indices. They're supposed to be indices. And the main thing you want to remember is that they're ordered. So they actually have to be in the same sequence as they are in the original array. So such that AIAL, so now we're looking at the actual values, right? So we're looking at the actual values so that I1, AI2, AI, AIL, right? So these are the actual values corresponding to indices. They are also strictly increasing, right? So this is like looking at the values in the array. If you look at only these, so if you look, at A0 and then A4 and then A7 and then, A10 and A20, if you look at these values, these are also strictly increasing. Okay, so what we're looking for is so this would be a valid increasing subsequence. So it's a subsequence because the indices are in order, right? So we're not rearranging the order of the original. It's increasing because the values are increasing, strictly increasing, right? And then what we want to do is we want to find the longest one, right? So they actually give us an example as well. So you should, take a look at that. They say, suppose that A is given by this array, then the longest increasing subsequence is actually given by the indices 1, 3, and 6. Right? So we actually have the indices 1, 3, and 6. So again, if you notice, these are increasing. So again, these are our indices, right? So they index into it, which means what we know, it should be true that A3 and A6, right? So we use these to look up the values. It should be true that these are also increasing. So if you look at A1, that's actually 3. You look at A3, that's 5. And then you look at A6 and that's 8, right? So you have 3, 5, 8. So it is increasing. And the claim is that this is actually the longest one you can have that has all these properties, right? Because if you take the 6, then, basically all of these get ruled out. You cannot look at them anymore because they're all smaller. So then you have to take the 8, right? So if you start with 6, then it's got to be the 8. So you're like, oh, let's not take the 6. Let's take the 3, right? Which is what we did here. We took the 1 index 1, so we took the 3. So that actually will eventually give you this one. But you say like, oh, why can't I take the 2? Well, it's because if the 2 is index 3 here. So you would say, let's take index 3. And then you look forward and you see like, well, what's bigger? Well, 5 is bigger, 6 is bigger. So this is also another valid sequence. 3, 4, 5 is also valid because that gives you the indices 3, 4, 5 give you 2, 5, 6 as the values. And that is an increasing 2, 5, 6, 8. Actually, 2, 5, 6, 8. So this is actually longer. Let's actually see. So this is 1. So the indices 2, 5, 6, 2, 5, 6, 8. Oh, actually, I think the homework is 3, 5, 6, 8. So this is 3, 5. Oh, the indices are 1, 3, 4, 6. 1, 3, 4, 6, which is a 4, a 6, which is 3, 5, 6, 8, right? So this is length 4. This is also a valid subsequence. What is this? This is 3, 4, 5, 7, 6. 3, 4, 5, 6, right? They're both valid increasing subsequences, and it turns out they're both the same length. They're 4, length 4. There is no greater length, right? So you know that you can see that in this example pretty easily, because if you start with the 5, then like the most you're going to get is 4, right? So you have to start with at least 2, but we already checked, like if we start with 2, we can't take, we can take the 5, we can take the 6, we can take the 4. We can't take the 4 because it's 2, it goes down, right? So either 2, 4, 8 is one option, or 2, 5, 6, 8 is the other option. And that's basically it. Those are your longest ones. And then 6 is too big. So that's the example. And we're going to walk through the recipe that we saw in class, right? So if you guys remember, the recipe has several steps to develop an O of n squared algorithm to find the longest increasing subsequence. And just FYI, there's actually an O and log n, right? So dynamic programming doesn't guarantee you that you're going to get sort of like the fastest algorithm. There's actually a divide and conquer algorithm that is n log n. But with dynamic programming, we'll be able to get an n squared one, which is, not too terrible. It's not terrible. So let's go ahead and get started on that. So part 1, if you notice, so 1.1 here says we first want to identify the optimal substructure and the recursive relationship. And actually what I did here is I gave you the substructure. So we said, let's come up with the subproblems and a recursive relationship for you, although you have to justify it. So you have to tell me why this works. So I say, let di be the length of the longest increasing subsequence from A0 to AI, right? So again, instead of, we have an array with a bunch of numbers. So again, let's look at this example. Right, this is A. And now what I'm saying is like, well, define di, right? So there's going to be another array of like subproblems. This is the longest increasing, the LIS, longest increasing subsequence from A0 up to and including AI, right? So when you say D0, this corresponds to the array A equals empty, right? D1 corresponds to the array given, let's not say equal, let's say given by just the 6, just the value 6, right? D2 is saying, what is the longest increasing subsequence of 6, 6, 3? And so on and so forth, right? Where you have like D3 is going to tell you what is the longest increasing subsequence of 6, 3, 2, okay? And then D4, is going to tell you what is the longest increasing subsequence of 6, 3, 2, 5, right? And so on, where you can imagine that eventually D1, 2, 3, 1, 2, 3, 4, 5, 6, 7, D7 is going to tell you, it's just going to give you what is the longest increasing subsequence of the whole thing, right? So that's, I'm telling you, these are your sub problems. So you're actually going to have to solve all of these smaller problems, okay? And what you're trying to do is you're going to say, well, if I know the answer to D0, let's say I knew the answer to the longest increasing subsequence of an empty array, how does that help me solve the answer? How does that help me figure out what's the longest increasing subsequence of the array that only has 6? And then let's say I know the answer to the array that only has 6. How does that help me solve for the longest increasing subsequence of the array that has 6, 3, right? And one way to think about it is, well, this 3, you know, this 2, this 5, when you're thinking about making the problem bigger by 1, well, that number is either in your longest increasing subsequence or it's not, right? And those are your two choices. And whichever one makes your sequence bigger and is valid, then that's the choice you're going to take, right? But I basically tell you this. So, you know, let's look a little bit more. So I give you that subproblem, right? And then I want you to explain. I tell you this is the recurrence. This is the definition. This is how you calculate. You know, di, I tell you, is equal to the maximum of two things. Either dk, or I tell you it's equal to the maximum, okay, of, let's look at this, dk plus 1 from 0 to k less than I, less than or equal to k less than I. So this is basically saying, like, for all k from 0 up to I, okay, if ak is less than ai, okay, then I include it in this set, okay? And di is going to be the maximum of all of those, okay? So what I want you to do is I want you to explain, like, why is this the case? What does the above mean? Like a short informal description of why it makes sense that the, you know, so this is saying, this di, this is saying the longest increasing subsequence, the LIS, from A0 to I is di. And this is also equal, you know, the LIS from A0 I is also equal to the maximum of 1 plus D0, right? 1 plus D1, 1 plus D2, dot, 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 1 plus dk minus 1, okay? Or union, so here you have union 1, so 1. So we're actually going to take the maximum of all of these, but we only take this element. So we only say, you know, we include it as part of our maximum only if ak is less than ai. Okay, so what this means is, like, we take plus d0 only if a0 is less than ai. Okay, right, and then similarly here, only if if a1 is less than ai, do we take this value, right? And similar here, only if a k minus 1 is less than a I. Sorry, this is not k minus 1, it says I minus 1. Only if ai minus 1 is less than I minus 1. So we consider all of these values, and we take the maximum of that. Okay, so I want you to pause the video and think, like, okay, what do each of these values mean? Why are we taking the maximum over all of them? Okay, hopefully you paused the video and you spent a little bit of time thinking about, hey, like, why are we taking the maximum over all of these different values? Okay, and I think one way to notice this is that each of these values corresponds to a case, right? So this is saying, you know, we only look at this value if a0 is less than ai. So what this is saying is essentially saying, you know, let's focus on this first one here, right? What is this saying? This is saying our LIS, our longest increasing subsequence, is going to be the longest increasing subsequence ending at, index 0, right? Because D0. Okay, or let's generalize this. Let's say 1 plus dk only if ak is less than ai, and then we consider all k from 0 to I minus 1 inclusive, right? That's what the definition tells us here, right? That's what this means. We consider all of those, right? So if we look at this, what this means is, well, what we're really trying is we're saying, well, the longest increasing subsequence, right, up to, from A0 to AI is going to be, so the +1 here comes from, is going to be the longest increasing subsequence ending at index k, right? So that's the dk, right? That's dk. dk tells us longest increasing subsequence ending at index k, right? Plus we include ai, right? So we're saying, oh, one possibility is we take the longest increasing subsequence ending at dk, and then we include ai. So that's why we get 1, because that's including ai, plus dk, right? Because again, di is supposed to be the longest increasing subsequence from A0 to I, right? Yeah, and you notice here we also defined a di is the longest increasing subsequence from A0 to I that ends at AI. Okay, so this is actually important, that ends at AI, right? So here is di. This subsequence has to end at AI. So if it has to end at AI, it's basically 1, because we have to include AI, plus we're trying to figure out where is the previous element coming from. Like, where does the previous element come from? So we only look at previous elements that are smaller, right? So we iterate over all these k, and we say, well, if you're smaller, you could be the longest increasing subsequence, right? So maybe an example will help elucidate, but basically our longest increasing subsequence up to AI, including, that up to longest increasing subsequence that ends in the ith element is going to be the longest increasing subsequence ending at the kth element. So that's dk, for some value k smaller than I plus 1. And basically, and then we just take the maximum of all possible endpoints. Okay, so again, it always helps to have an example. So we can consider, again, this example, or let's try a smaller one. Let's say, let's say this example, D4. Okay, so we're trying to solve for D4, and we're saying, hey, what is the longest common subsequence here that ends with 5? Okay, so it has to end with 5. Well, the subsequence is going to be, it has to have 5 in it, so it's at least 5. So that's where we get the 1 plus. Okay, and then we're saying, well, it could be the one that ends at 2, right? So what is the length of the longest common subsequence here that ends at 2? It's actually 1, because if it has to end at 2, it includes 2, but that means it cannot include 6 or 3, right? So this is 1 because it ends at 2. The other option is we have 5, so that's 1 plus, and then the subsequence that ends at 3. So again, that one is also 1 because it, ends at 3 and it can't include the 6, right? But let's say we had a 1 here. Let's say we had a 4 here, right? So now when we get to 6, we see, well, and notice that the 4 doesn't change the answer for these because 2 and 3 are both smaller than 4, so the subsequence doesn't get any bigger. Then it's going to be 5, when that's 1, plus what is the longest subsequence that ends at 6? And the answer here is, well, if we take 6, the longest subsequence is actually 4, 6. So that's actually 2, right? So it's actually both 6, or actually, it can't be 6. We can't look at 6 because 6 is not smaller than 5, so we actually don't even look at this subsequence. So let's say this had a 3 here. Then we would say, well, now we look at 4, which is smaller than 5, so it's valid. We take it, and we say, well, we have 5, and then 1 plus what's the longest subsequence that ends at 4? Well, the longest subsequence is actually 2, because it consists of 4 and 2, right? And ideally, we already have this answer. We don't actually have to recompute it, right? And then we also ask, well, what if I end at 3, right? Well, at 3, the longest subsequence is just going to be 1 plus 1, because it's only 3. But you can imagine, like, you might not want to take the 4, right? Like the same way here, you know, it's possible that this 6, like if you take the 4, it's possible that you have like a lot of, let's say 3.5s here, or say you have you would rather take the 3. Yeah, I mean, there's many different ways to solve this, but this is one approach, okay? And that's basically the justification for this recurrence relation. Now, the next question asks you, like, you know, develop a dynamic programming algorithm. So use the relationship to design a dynamic programming algorithm that finds the length of the longest increasing subsequence, right? You just need the pseudocode, no justification required, you know, so this one should be pretty straightforward, right? I already gave you the relationship, so even if you don't know why this is true, then you should try to write that in code, right? So basically we say, well, D, you know, D is, you know, we have D0 is equal to 0, right? Because, or sorry, D0 is equal to A0, so, or is equal to 1, because the longest common, you know, the longest increasing subsequence that ends with A0 is of length 1, right? And now we have a for loop. So we go for, you know, I equals, or yeah, for I equals 1 to, you know, the arrays of length n. So you go to n minus 1, right? So we're trying to fill this up. Then we have, well, di, right, is going to be equal to the maximum of all of these values union with 1. So di always starts at 1 because it's always at least length 1. And then we try to find the maximum for all possible values of k. So we say, you know, for, you know, k equal to 0 to I minus 1, right? So again, this is inclusive. So this is going to include I minus 1 as a value, right? Because we go from 0 to I minus to I, not including I. Then, you know, di is the max of di, right? Either itself or the other option, 1 plus dk. Right. So that fills up your array D, right, of size n. And then once you filled it up, that means, you know, di now tells you the longest increasing subsequence that ends at ai, right? So now the actual value of the largest increasing subsequence anywhere, it could end anywhere. It doesn't have to end at the last, you know, so if I just, like, you might say, like, oh, I just returned d n minus 1, right? Where we say, you know, n equals the length of a, right? But this is actually just the longest increasing subsequence that ends at n minus 1, right? But that's not actually what we want. We want the largest increasing subsequence anywhere, right? So you would actually just, you know, return the maximum of all the d's. So you return max of d. For all the values inside of the array D, get the biggest one. That's your answer. Okay. So that's the pseudocode for part 4. Okay. No justification required. You just need a pseudocode. But now the last thing is I want you to modify your DP algorithm to actually return the optimal solution, right? So instead of just telling me the length, right? So this is just going to tell me the length of the longest increasing subsequence. I want you to actually tell me the longest subsequence, right? So this is algorithm 1 takes a as input. So we're going to have our input is an array a, right? And it's going to return our output is the length of the LIS, longest increasing subsequence, right? That's the algorithm we just finished. So what we want now, let me open a new tab so I can save some of this stuff. Let's do this. And then let's let's bring back the answer he had for 1.1. So I'm actually going to save all of these so that I can use them to actually type up the solutions. So we undo here. Let's see. Sorry, I'm still undoing. Okay, I think this is basically the answer to 1.1. So I'm going to make sure I've got everything written down. Okay, there we go. And let's get started on 1.3, right? So this is what we have for 1.3. Again, longest common subsequence. This is 1.3. And all it asks you to do is, like, instead of take this algorithm that you wrote for 1.2 and now modify it so that it actually tells you the longest increasing subsequence, right? So now the output is not going to be the length of the longest increasing subsequence. It's going to be the longest increasing subsequence. So the set of indices I that make up the LIS, right? Or the values themselves, right? However you want to do. So let's do the values, right? The values, right? But it's actually pretty easy to modify, you can imagine, right? Because basically what you're trying to figure out is once you know where the longest increasing subsequence ends, then you just need to figure out where did that ending value previously come from, right? So looking at this, you have DI. So DI, in a sense, the biggest value for this DI is telling you the last, the index of the last element, because DI is the longest increasing subsequence that ends at AI. So once you find the biggest value here, that tells you the index of the element at the end of the longest increasing subsequence, right? So all you need to know now, because DI tells you the end of the longest increasing subsequence at a particular point, is you need to know what was the index of the longest increasing subsequence I came from before, right? Like where did I come from? And actually, you can figure that all out from your DI, because once you have the maximum value, that tells you where the subsequence ends, you just need to look backwards to find where is the next biggest value of DI, right? So in a sense, what we're going to do is we're going to use D to rebuild our subsequence. And what I mean by that is you can do a for loop where you iterate so the algorithm is already O of n squared, right? So we're going to do two for loops, nested for loops, where we find the maximum, and then we find the maximum only up to the point we found the maximum. So we keep finding the maximum value, but only up to the point where we found the maximum, right? That's one way to do it. The other way to do it is you can actually modify the algorithm here when you are actually finding the maximums to keep track of so you could keep track of, so DI you fill in, and it tells you that that is the index of the last element. So I'll let you guys pause the video and maybe think about this for a second while I also try to think about it. You should be able to, there's definitely an O of n squared solution to reconstruct the elements, but I'm trying to think if there is a faster way to use, I mean, it's not even going to be faster because big O, it's the same, but maybe there's a linear time way to just reconstruct this by keeping a little bit of extra information. So I think we can keep track of the K index that we came from for each value, and then we can immediately reconstruct it. So let's do the second option first. So the second option says, in addition to D, right? So we had, in addition to where we had D0 equals 1, right? We're also going to do a pref of 0 here, and we're going to set this to -1. So pref is going to start -1. It's going to be of size n, same as d, of size n. But what we're going to say is that pref I is going to represent the kth index that we came from when we ended the LIS at I. Okay? So essentially what this is going to be is this is going to be the k value that actually gave us the maximum, right? So now what we're going to do is we're going to modify this inner loop. We're going to say, well, if 1 plus dk is bigger than di, right, then di gets updated to dk, okay? And we're also going to say here like di here is -1, which is saying the longest increasing subsequence is just myself, and I came from nowhere. I like ended, right? It was just me. That was it. It was the longest increasing subsequence. We're going to use -1 to represent that. So we're going to say this pref, pref of I. That's where it starts. It starts at -1. But then every time we find a k value that actually gives us a longer increasing subsequence, we also update pref I to be k. So now pref I is going to tell us, oh, it's actually k, right? So now what we do is now when we're done, we just say, well, like find the maximum index of d, right? So we say max index equals -1 or whatever. I mean, there's going to be one. So let's say max index equals 0. We'll start there. And we say for, I equals 1 to n minus 1, if d, I is bigger than d max index, then max index equals I. And then when you're done, max index is going to point you to the biggest value. So that's where you're, that is the index where you ended. So now we're actually going to try to reconstruct our longest increasing subsequence. So we're going to say our longest increasing subsequence, and we're going to say the values, right? So not the indices, the values. Which it's basically the same because you can just grab them. So we're going to start this at 0, right, or as an empty string, right, or an empty array. And we're going to say, okay, while pref of max index. So we actually don't start it at 0. Sorry, we started at a of max index. So we know we end here, okay? And while this is not -1, so while we still have a previous thing, then max index is going to be pref of max index. We're going to go to the index where we came from, to the k that brought us here, right? So in this for loop, we're going to go back to the k that brought us here, and we're going to say, oh, you are the next element in our longest increasing subsequence, right? So that's why we're setting you to the max index. Let's add you. We could say pushback because it's an array. Let's add you to the longest increasing subsequence, LIS, a max index, something like this. And then we keep going, right? So we have updated max index. Now we go and we say, well, if you're not -1, that means there's still somebody, right? So we go back to you. We add whoever you are. Then we keep going, we keep going. And then at the end, we return the reverse of A, because it's the way I defined it. In this case, it's backwards. Okay, so this is one option, one version of the pseudocode for reconstructing the actual LIS. Another option for the pseudocode, like we talked about just a few seconds ago, is you can actually not keep track of the pref, right? So so let's talk about running time, right? So these two nested for loops are going to be n squared, right? Because that's just how long it takes, and they're going to use O of n space. This part here, finding the maximum, like this is going to be O of n. We know that. We have one for loop. We're just comparing values. This while loop, like you're always going back, back, back. So at most, you see every element. So this is also at most O of n before you get to like a -1, right? Because there's nowhere else to go back to. So that means, O of n, O of n. So the total running time is O of n squared. The total space is O of n, right? Another option is you don't have to do this. You don't have to keep pref. you can reconstruct the whole thing just from D. And the way you can do that is you can say, let's just go back to our easy, equals max of 1 plus dk or di, right? Let's just go to our easy version here, and you can just say, well, let me actually find the maximum of d, right? Let me find the max of d. So this is going to be, my LIS, right? So again, LIS is going to be empty. Let me find the maximum index of d first. So you would say, okay, for, max index equals 0, for I equals 1 to n minus 1, if di is bigger than d of max index, then, I equals max index, right? Or sorry, max index equals I, right? And then you would say, well, my LIS starts here, okay? So it starts with A at max index, okay? And then essentially what you do is you repeat this process, but now your ending, instead of your ending being n minus 1, your ending is going to be the max index, because you're looking at everything that came before you and you're trying to find the biggest value, right? So essentially this is going to be nested in a for loop, right? So we're actually going to have ending, it's going to start at n minus 1. So we're going to do from I equals 1 to ending. Yeah. And we're going to do, max index is 0 from, and we iterate from 1 up to ending, where ending is n minus 1 at first. And we do this. Oh, actually, this won't quite work because you won't know. You won't know. Oh, you're actually just looking for the minus 1. Oh, it's actually so much easier than that. Okay. You find, I think, yeah, you find your max index, and then you can actually just iterate backwards over D. So from I equals max index minus 1 to 0. And then any time that D I minus 1, okay, let's go up to 1. I minus 1 equals DI minus 1. So anytime it decreases by 1, that value is in your, because the length will be like 1 smaller. So I think you can take that value. Yeah, actually, you guys think about that a little longer. I'm more confident in the first solution, but I'm sure there's a way to do this better. So let's jump to the next question, 1.4. And this is the last one, adapt your algorithm to find the actual LCS. Oh, that's 1.3. So we're actually done with that. Question 2. So we're on question 2 now. And it says, let's get greedy. Sometimes it can be difficult to know if a greedy algorithm works. So here we give you a problem, say whether or not the greedy solution will work. If it wouldn't, give a counterexample. So here's a problem. You have unlimited objects of different sizes, and you want to completely fill a bag with as few objects as possible. Okay, so what we say is the greedy solution is keep putting the biggest object first as long as it fits. Okay, so it's like I have a bag of a certain size. I want to fit as many objects as possible. Okay. Oh, I want to completely, actually, yeah, the goal, so this is my problem. I have a bag of certain size. I have unlimited objects of different sizes. Okay, so now we're talking about sizes, not weights. These are sizes. My goal is completely fill the bag. Like, have as much of the volume taken up by the objects, right? And the proposal is take the object that is closest to completely filling up the bag first. and then, and then repeat. Like look over all the objects, take the one that fills up the back the most, even if not completely, that still fits inside, but doesn't fully fit it. And then keep going. And you guys should pause for this. It's not a very hard problem, but it's an example of like when a greedy solution doesn't work. And this is like really good to catch because you probably don't want to use a greedy solution here. But basically, let's say my bag can fit, 10 units of stuff, right? And let's say I have objects that take, 9 units, 5 units, and 5 units, right? Like obviously, like by this algorithm, I take the 9, or not even the 9. Let's make it even worse. Let's say 6. This is 6, right? So by this algorithm, I take the 6. Okay, so I have 4 left, 4 units of space. I can take nothing else. So my bag actually only fit the one object, but not even that. It didn't even fill up completely. It has 4 units of empty space, right? The actual solution is take the 2 5s, right? So again, it's not hard to come up with a counterexample as to why this algorithm doesn't work. But that's, it's the assignment, it's 5 points. So you guys give that a shot, just think about it. Okay, moving on to the next one. We're on question 3. So this is a housing layout. This is a dynamic programming problem, okay? We're gonna walk again through all the different steps, okay? So this is the recipe for dynamic programming. We're gonna walk through each of them. Yeah, so the way the problem works, and to be honest with you, problem should remind you a lot of pick berries. Okay, so if like go look at that solution, go think about that problem. This is from homework 2. There we just used recursion. We did not use dynamic programming. So that solution is actually really, really slow. Here we're going to use dynamic programming. Okay, so to get started, you say, okay, I'll have a housing layout with n greater than 1 consecutive plots of land. You can build up if you want to build up. Has at most 1 house. However, due to some strange laws in your city, you cannot build 2 houses and 2 consecutive plots of land, right? So you can't pick the berries from a bush that are next to each other. You can't build houses on, 2 places that are next to each other, okay? Each plot of land is different, so in some buildings are more important than others, okay? You have actually estimated the profit from each plot of land given by an array P1 through Pn, where the ith plot of land tells you that is. So here's the example. So if this is the array 21, 4, 6, 20, that tells you, hey, if I build here, I'll get $21 in profit. If I build in the second spot, I'll get $4. If I build in the third spot, I'll get $6. Now the restriction is you cannot build in spots that are next to each other because then the neighbors get unhappy, whatever story you want to tell yourself, right? Again, it should really remind you of pick berries. Very similar approach, very similar solution. The optimal solution here is actually to build the first one, get the 21 in profit, build this middle one, get this third one, get the 20 in profit, and then build the very last one, get the 5 in profit, because that actually gives you $46, okay? However, you might think like, wait, actually, I want to build this 6 in profit. Well, you can't build the 6 because it's next to the 20, right? And then similarly, this is an example. This is not valid. You cannot build 2 houses next to each other, okay? But now we're gonna solve this using dynamic programming instead of recursion without memoization, right? So step 1 is optimal substructure. What subproblems will you use in this dynamic programming algorithm? Okay, to get you started, let's define PI. So let's define PI, says 3.1. Let's define PI as an array of length n, okay, which has all nulls, okay, to start out with. So you're going to have an array P that's going to be your answers. It's the same length as your input. It's going to be, everything is going to be null. Now the question is, what does PI represent? What subproblem is it? Okay. So again, I encourage you to pause the video, think about this, see if you can figure it out. It should be a smaller problem than the original problem, but it should be something where the answer to the original problem can be solved once you have all of the PIs. So once you know the answer for every single PI, every value in the array, then that should help you figure out the answer to the original problem. Okay. All right. Cool. Okay, so one way to approach this is to say, well, PI is the maximum profit PI is the maximum profit, right? So what's the actual problem we're trying to solve? The actual problem is like, given the array of houses, what is the maximum profit I can make, right? So that's what we're trying to solve. And one way to define PI is as the maximum profit as the maximum profit for the array of houses A1 to, or sorry, it's not A, they're called P, so lowercase p, P1 to ... I. So how much profit can you make if you have access to the 1 to the ith house, right? And the idea here is like, if you define it this way, it's actually easy for you to figure out, what is the maximum profit I can make, right? So we say PI is the maximum profit for the array of houses from P1 to PI. Okay, so that's very similar to the previous problem. Hopefully that makes sense to you. You can also define it the other way. So you can say like, you could define it backwards, I guess, as like the maximum profit for the array of houses P I ... up to n. So from I up to n, and you can like work backwards, or you can define it from 1 up to I, and you can like fill it in forwards, right? So it kind of depends how you define it. We're going to go with the forwards one, just because like, why not? Okay. So that's 3.1. 3.2 asks for the recursive relation. So once you've defined PI, it tells you, well, how do you compute PI? How would you use answers to smaller problems, aka, in our case, PI minus 1, PI minus 2. These are smaller problems, right? Because PI minus 1, given our definition, is like, oh, what's the maximum profit for the houses from 1 up to I minus 1? PI minus 2 is like smaller because it's like, oh, what's the maximum profit for the houses from 1 up to I minus 2, right? So these are smaller problems in our case. So it's basically, okay, how can I figure out the maximum profit for all the houses from 1 to I using the answers to the maximum profit for all the houses from I to I minus 1 or I minus 2? And I'll say, well, you basically, you're going to take the maximum. Maybe I'll encourage you to pause to think about what are some possibilities here, but I'll tell you this, there's 2 cases. Okay. Easy cases. Okay. Case 1, I build the ith house. Okay. That's case 1. Okay. You build it. So what does that mean? If I build the ith house, then that means I get the profit from the ith house, plus I cannot build the I minus 1 house. So I have to get the profit for everything up to the I minus 2 house, right? Like if I want to build all the, this does not include the I minus 2 house, but I'm saying, like, again, PI, if you guys remember from the previous problem, is the maximum profit that you can make for this problem, right? So PI is the maximum profit for the array of houses from P1 to I, right? So if I'm trying to figure out what's the maximum profit for houses from 1 to I can say there's 2 cases. Either I build the ith house, which gives me profit small p I plus capital P I minus 2, because I know that I will not build the I minus 1 house because I already built the ith one, right? So I'm just saying like, well, what's the maximum profit I can make from everything that comes before it, right? Because these I can still build. So just tell me, what's the maximum I can build from these? Don't do I minus 1 and then do I. The other option is case 2. I don't build the ith house. So then I can just look at P, capital P. I probably should have used different letters. Capital P, I minus 1. because basically I'm saying, well, I'm not going to build the ith one. That means like just basically the maximum profit I can make if I don't build the ith one, up to the ith is what's the maximum profit I can make up to the ith minus 1, right? These are the two cases, and you take whichever one's bigger. Like, is it more profitable to build it, or is it less profitable, or more profitable not to build it? So whichever of these two is bigger, that's the one you take, and those are your two cases, right? So that is your recursive relationship, okay? And again, it depends on how you define your problem. You might maybe use I plus 1, I plus 2, or use I minus 1, I minus 2, right? But now we jump to 3.3, and here, I just asked you for the base cases. So what are the easy solutions? So again, if you go back to PI here, if you go to this problem statement, PI is the maximum profit for the array of houses P1 ... up to I. Then I would ask you, what is the easiest solution you already know the answer to? And we would say, well, P0 is 0. Okay, because that's saying P0 is saying, what is the maximum profit for the array of houses P1 up to 0, which is the empty array, right? Because you go from 1 to 0, which means there's actually nothing in it, right? And in that case, the maximum profit you can make is 0, right? So P0 is 0. That's where you start. And you need another base case, actually, because if you notice in your original problem, you actually do I minus 2 and I minus 1. So if you try to solve for 1, you'll go to 0 and you'll go to -1, right? But one easy way to do this would just be, well, P1, right? So if maximum profit for the array of houses where it's just the first house, right? That's just the max of 0 and the value you could get from building that first house, right? So again, that's an easy case, right? Because you either build that one house or you don't build it. That's it, right? So now that you have these two, then you can start very easily iterating. To be honest, you can also do something where you can say P -1 equals 0 and drop this base case. As long as you get 2 zeros here, 2 base cases, so that you don't index out of bounds or whatever, it'll work. But in your code, you're probably going to just solve the answer for 1 and then just start with I equals 2, right? Right, so now we get to step 3. So we jump to 3.4. And we're saying, hey, the algorithm, now write the pseudocode, right? So this should be pretty easy. So I want pseudocode, and honestly, you can drop the English description. You don't need to justify if it's correct. It's pretty easy. But I want you a dynamic programming version. So you can do top down, you can do bottom up, you can do whichever one you want. But take a look at the slides. This is good practice for you. Hopefully it's not super challenging, but we'll walk through it. So pause the video, think about it, and then I'll go ahead and walk through the solution. So now that you're back, hopefully you thought about this, you took a stab on your own, maybe you did the top down, maybe you did the bottom up, right? So I'm going to do the bottom up. Top down is pretty easy too. It's actually easier, I would say, but I like bottom up just because I personally want to practice bottom up, right? So what you would do is you would say you do your base cases first. So let's say, algorithm, you're going to be given P, which is going to be the profits, and, input P. P is the one indexed profits from the house, right? So remember, according to our problem, we start with like P1 is like our 0th house, or like whatever. It's one index. It starts at 1, right? It's kind of weird, but that's how the problem is given. Then the output is going to be the maximum profit. Okay, profit we can make by building houses according to the rules given, right? So we first say, well, P, let's say P. P is going to be a bunch of zeros. So sure, we'll do a little bit of C++. Why not? We like to code. So we're almost going to write this as opposed to real code. So P is just going to be a vector of integers of size, P dot size plus 1. Right? It's going to be 1 bigger, just because we like it that way. Okay, so that's going to be our P, like our capital P, right, that we were talking about. And then we have our base case, so P0 is 0, and we have, P1 is the max of 0 and P1, whatever. Let's just call max. Let's not use standard. Let's just say whatever. Let's say this. It's fine. You guys get what I'm trying to do, right? And then we fill it in. We fill it in from the bottom. If you did it the other way, you would fill it in from the end going backwards. I did it this way, so I say, for I equals to 2 to n. So actually this is inclusive. Again, we are going to include n because things are one index, right? I'm going to say capital P of I is going to be equal to the max of 2 values. Either I build a house, so it's going to be Pi plus capital P of I minus 2, or it's going to be capital P of I minus 1. Okay. And then at the end, I'm going to return P of n. And that's it. Makes sense? That's it. Very simple algorithm, just the for loop. Running time, right? You can probably figure this out, just the for loop, this O of n. The space is O of n, because you have to fill in the P. So that's it, and you can describe it if you want, but that's it for 3.4. 3.5, very interesting problem. It asks you, where do you build? So again, the whole goal is to modify this algorithm now to also not tell me just what's the maximum profit, but tell me where do I build the houses. This is actually not as hard as you guys think. So we can just return a vector of indices, right? So it's like not the maximum profit, but like where to build, which houses to build, which houses to build to maximize profit, right? So I'm just going to return the indices. And in general, you can follow a similar strategy where, like, essentially Pn tells you, like, if I want to build up to and including I, like, you basically want to know when did the max value actually take the first branch, right? So as you iterated through the array and you were building it up, when did you actually pick to build that house versus not build it? So this is actually a lot simpler. So you can say, build is just an array. So the very first thing you would do is actually, you would declare your build array here. So it's just empty. And then the very first thing is you would say if, yeah. So this is fine. Yeah, you want to keep, so at minimum you want to keep, like, build starts as empty. Basically you change this to an if statement. So if Pi plus Pi minus 2 is bigger than Pi minus 1, then that means you do want to build the ith one. So you say build pushback I. Okay. And you also say, Pi equals this. The issue is that's for Pi. Yeah, so I think we're actually going to need to keep track of a pref again. So pref is like where did you come from, given that you built at the end, right? So this is going to be it's going to be similar to P, but we're just going to call it pref, and we're going to set all the values that we have, right? So here we would set, the pref of 0 is going to be -1. Here the pref, we can change this to an if statement. So if P1 is bigger than 0, then the pref actually, in both cases, the pref of 1 is also -1, right? Because you didn't come from, the last house you built was unknown. And then we fill this pref in as we do this. So when we have this if statement, we're going to have, this pi gets updated, but we're also going to update pref I to be equal to I minus 2, because, well, you don't know that you built I minus 2, but that's where you want to look to see what you actually built. And if it's -1, then you don't take it. Yeah, something like that. Actually, I'll let you guys think about this one. Good luck. All right, let's look at 3.5. Sorry, 3.6. So 3.6 is actually saving space. So the space complexity of your proposal should be pretty clear. We talked about this. It's O of n. You should notice that if I'm only asking you for the maximum value here, so this pseudocode, you'll notice that pi only ever depends on pi minus 2 and pi minus 1. So there's only 2 previous values that you need to keep around. So it's very possible to modify the solution so you don't have to keep this vector p, like the whole vector. So I encourage you to do that for 3.6. All right, let's jump over to the coding now. So again, the coding is available both in C++ and C++ and Python. You're more than welcome to do either one. The autograder is all set up. It should solve both of them. So if we take a look at the coding here, there's actually 4 problems. And to be completely direct with you guys, like each of these problems corresponds directly to a problem that we covered in class. Your job is simply to actually implement those solutions. Okay, so I'll go ahead and walk you guys through it, but I really think you guys can do this. The first problem is just longest common subsequence, but I give it a different name. I call it len shared password. Okay. The second problem is transporting valuable material. This is unbounded knapsack, but I just give it a different name. And the third problem is bounded knapsack, the 0-1 knapsack, but again, I give it a different name. And the fourth problem is plumbing pipes. This is actually maximum independent set on trees, but I give it a different name. Okay, so I encourage you guys to read through in detail each of these pieces. Hopefully it doesn't take more than an hour or two. And then actually try to implement them. So again, the goal is just to implement these here. And we can just jump right in. So again, I hope you guys pause the video and maybe you're coming back to this later. But this is actually just LCS, longest common subsequence. And the thing to remember for LCS is that you have Cij is equal to, there's two cases. It's the maximum. Oh, well, there's actually 2 cases. This is the key, right? There's 2 cases, Cij. And there's 2 cases. Case 1 is Si equals, Tj, right? So the characters match. In that case, it's 1 plus Ci minus 1, j minus 1. And there's another case where they don't match. So case 2 is Si does not equal Tj, so the characters don't match. In that case, you want to take the maximum of either your smaller subproblem, Ci minus 1 j, or Ci j minus 1, right? So as long as you know this is pretty easy to implement, top down, bottom up, whatever you want. I want to practice bottom up, so I'll probably do that. But really, the basic thing is you want to initialize your array C. So again, one way to do this is you can use vectors, you can use unordered maps, you can use whatever data structure you want to store your values. I'm going to use a vector of vectors here of integers. I'm going to call it C. And a really easy way to initialize all of this to 0, because again, the base case is zeros, is you can just tell it how big you want it. So one thing to keep in mind is that this needs to be 1 bigger than the actual size of the strings, because the strings are 1 index, but the array is 0 index, right? And we have these like columns that go the column and the row that is all zeros. So again, I encourage you guys to take a look at, we're basically implementing the algorithm that we covered in lecture 26. So hopefully this is not too difficult for you guys. But if you go, if you open up lecture 26, I think I linked to this actually in the README. So I think there's actually a link here. Well, I linked to 26 and I say, slide 15. So if you open up lecture 26 and you look at slide 15, you're implementing this. This is your pseudocode for the least common subsequence. So you need to understand this. Okay, I don't want you to just copy it. Like, first of all, if you just copy it, you're going to get it wrong. You're going to struggle a lot. Try to understand it. Okay, like just because the pseudocode is here, it doesn't mean all of the work is done. It's actually pretty hard to implement these algorithms, but I'm sure you guys can do it. That would be step one. So you're just trying to implement this, and that's what we're going to do right now, right? So the couple of things you need to know is you set, like I said, you have this giant matrix. You set all these to 0, right? And you also set, as you notice, like for this example, y is length 4, but the matrix is actually of size 5 by 6 instead of 4 by 5. Right, so it's 1 bigger. So that's something to notice because that actually matters. So when you write it, you make it 1 bigger, right? So this is the syntax for creating a matrix of just a bunch of zeros of size s by t, s plus 1 by t plus 1. So t dot size plus 1. So this creates this one line of code. Whatever this is. Let's make this smaller. This one line of code creates a matrix of size length s plus 1 by length t plus 1 filled with zeros. Okay, that's what this does. So that actually covers our base cases. So now we just fill it in. So again, you can go look at the pseudocode that we have here, but basically you iterate over both indices of s and t, and for each index, you see if they match up. And then because we have this recurrence relation, you should be able to just calculate it by taking a max, right? So you would say, for int I equals 1, or you can say 0, but you have to, like, the one thing you want to remember is that your storage is like off by 1, because in the lecture slides, okay, this part where we say xi equals yj, that's 1 indexed, okay? So when I do like x1 here, that corresponds to a, which in your code is actually x0 to get to a, right? So again, this is what I mean, like you really want to actually understand the solutions because it's not just as easy as like copy pasting what we said. But anyway, one option is you iterate. We could do this. We can iterate starting at 1, and we go, I is less than or equal to s dot size. So again, less than or equal to matters. Starting at 1 matters. You can start at 0. You can make it less than. There's many options for how to do this. And then you have your j. So this also starts at 1, and then j is less than or equal to t dot size, and then j plus plus. So these are your 2 for loops, and then you fill it in. So you have c, I, j. That's what you're trying to answer. But you have a couple of cases, right? Like we said, the first case is they are equal. So if s I minus 1 equals t j minus 1, right? And again, I have to do minus 1 because the first character is actually 0 indexed in S, but it's 1 indexed in my matrix. Okay, so just keep that in mind, but that's this case. So if they're equal, right, because when I said SI equals TJ, this is 1 indexed. When I'm writing it in code, arrays are 0 indexed, right? Then this is 1, then that means Cij is equal to 1 plus Ci minus 1. J minus 1, right? Otherwise, the other case, it means that Cij is equal to the maximum of Cij minus 1, Ci minus 1, j. Okay, very simple code, actually. Very hard to understand. Very simple code. And then at the end, we return C s dot size. t.size, right? Again, C is, in a way, it's one index, but it's basically one bigger. And then you can actually run this code, and you'll see it works perfectly. It's not working perfectly fine. I'm actually getting 0, 0, 0 for all of these, which is not the correct answer. So I suspect, it's my else case. I had, so I don't know if you guys saw this, but this else is actually, I was always executing this, which is wrong. So it actually needs to be the else like that. And ci j I minus 1 j j j j I. Okay, let's try that. And yes, that was the bug. So I don't know if you guys saw it, but maybe hopefully you saw it. Everybody makes mistakes. The bug is that I had the curly brace here. So my else statement was doing nothing. And then I was always executing this max. So I think that was basically erasing a bunch of stuff in my matrix. So obviously it's wrong. But yeah, there you go. And transport value, again, this is similarly pretty straightforward, I would say. Not super crazy, but I point you guys, I tell you, hey, if you're having a lot of trouble with this, Q1, take a look at lecture 26, slide 42. So again, if you scroll down to slide 42 here, you're basically coding this up. It's unbounded knapsacks. It has different, you have to figure out what the values are, what they represent. I don't give you n, but if you understand the problem, it's pretty obvious what n is. And then the rest of it is just like you have to code it up, right? So again, we can do this together, but I encourage you to try it. The very first thing you do is you can assume that dollars and pounds are going to match. They're going to be the same length. I'm not going to give you examples where they're different lengths because that doesn't make sense for the problem, right? What you do know is that your n. So your n is actually going to be given by dollars.size or pounds.size, because pounds is how much the item weighs, dollars is how much it's worth, right? And then vehicle capacity is your W, right? And then again, like you want a storage vector. So this is int k, which as we saw here. So if you go here and you walk through the example, you'll notice that k, we have 4 items, but k is actually of size 5. So it's one bigger because we start with the 0 having 0, right? So k is 1 index. So this is 1 bigger than n. So this is n plus 1. And then what you do is you iterate over all possible, you start filling in k. So you start, for the pseudocode uses x, so x equals 1. X is less than or equal to vehicle k. Oh, sorry. So k is actually related to your capacity. I knew I was doing something wrong. So k is actually your vehicle capacity plus 1, because you fill it in for all possible backpack sizes, not for all possible items. So as long as this is bigger than or equal to vehicle capacity, then you x plus plus, right? So this is your for loop trying to fill it in, which is hey, what if I have a backpack that can only fit 1 pound, right? What if I have a backpack that can only fit 2 pounds, right? And the main idea is that if you guys remember, hopefully from lecture, the optimal value for a backpack, we're trying to figure out kx. So it says I have a backpack that can fit x pounds, right? That's actually given, but again, there's basically 2 cases. You have kx is equal to, or not 2 cases, because this is the unbounded knapsack. You're basically saying for all items I, for all possible items, take the maximum over, well, if I can fit that item, so if the item weight, which is the weight, wi, is less than or equal to x, so if it fits in the backpack, consider taking it. So that's going to give me value I dollars, because I took it, plus how much can I fit in a backpack that can no longer fit the weight I, right? So you subtract WI. Because now you're saying like, hey, instead of how much can I fit in a backpack that fits X pounds, I'm actually going to try taking the ith item. So now I have a smaller backpack that cannot fit X pounds anymore, right? And that's if WI is less than X, and you take a maximum over all of these values, right? So one way to do that is you say, well, I'm trying to fill in, in code, you would say, well, I'm trying to fill in KX. And I'm going to set it to start at just KX minus 1, right? So this is the starting point. I'm not fitting anything extra. I'm just saying, like, hey, how much ever you could fit into the smaller backpack, that's the same you can fit into here, right? And then we try each item. So for, int I equals 0, I is less than weights.size, I plus plus, right? If the item fits, so if the weight, so this is not weights, it's called pounds. That's what I was not completing. So if the item fits, so if it's less than or equal to X, so if it fits in the backpack, then KX is equal to the maximum of whatever you had before. Like I don't want to ever get smaller, I just want to get bigger, plus the dollars, the maximum of that, or the dollars of item I, plus how much can I fit, K X minus pounds I, right? How much can I fit into the smaller backpack? So, but that's only if I can fit the item, right? If I can't fit the item, then I don't do this. And then I do this for every single item. Then I try the next weight, the next weight, the next weight, and you repeat this a bunch of times, right? And then at the end, you're just going to return K of vehicle capacity. So what is the biggest value I can get for a backpack of vehicle capacity size? Again, pretty straightforward code, and you can run it, and you'll see you can fit $8 that fits 4 pounds, and that's I believe that is the correct answer here. So pounds, you should be able to fit 8. So you should get 8. It gives a total value of 8. So at least for this, that's the correct answer. The next one, most price per session. So again, I give you a hint in the README, so I encourage you to take a look at that. Lecture 27 is one you look at, and you want to look at slide 22. So again, this is basically an implementation of bounded knapsack. So this is where we can't take multiple copies of the same item, where you can actually only take one copy of each item. So you want to scroll down to slide 22. Right here, you're looking at this pseudocode, and that's what you're trying to implement. But again, I encourage you really need to understand this, because first of all, this implementation is actually a 2D matrix that is a lot harder to try to understand. So you want to try it on your own and see how it works. It's honestly not that different from what you did before, but it's good practice, right? So again, we can do it together. You're going to have int n equals, in this case, let's say weights.size. Again, I'm not going to give you an example where the value and the weight are different sizes. They're going to be n is going to be the same size, okay? And again, what you're going to want to do is you're going to want to make your k, which is going to be this 2D matrix, right? 2D matrix of size w by n, right? Where n is the number of items. So again, the key to this problem, and hopefully you guys understand this, the key to actually coding this up and why it works, and you should understand this, is that when I'm trying to calculate, how many, so we have sub problems, kxi. So this is maximum value with a backpack of size x, of capacity x, when only considering items 1 through I, right? So I'm not even looking at all the items. I'm actually looking at less items, only 1 through I, and again, only for capacity x. So this is a much smaller problem. They're all problems that are the same as the original problem, but they're smaller problems, okay? And the other thing you should notice is our matrix is going to be 1 bigger, because we're going to have 0. So it's going to be 1 indexed, where we have weight 1 all the way up to weight w, right? But we also have a weight 0, because that's our base case. And then for I, we say items 1 through n. So I is going to go from 1 to n, but our items are 0 indexed. And also we're going to consider the case where we're not looking at any items. So we're looking at none of the items, not even just the first item, right? So hopefully you guys remember from the first problem here that you can actually pretty easily create a vector of vectors in one line of code. Let's call it K. And then this one is going to be, yeah, it's going to be W plus 1 by n, and then each element, each row is itself going to be a vector that is of size n plus 1 that has all zeros in it. So this gives you a W plus 1 by n plus 1 0 matrix, where everything is 0. And that actually, if you look at here, that actually covers your base cases because you needed to set all these values to 0 anyway, so you're kind of done with that. You just jump to the for loops. And the for loops are actually pretty straightforward here. So again, you have int x equals 1, so you're considering, backpacks of size 1. X is less than or equal to w because you go all the way up to and including w, x plus plus. And again, if we jump back to the pseudocode, you'll see that we consider all values of j, right? So now we say, well, what if we only look at the ith item, starting like the first item? So I is less than or equal to n, because again, the items are one indexed in the slides and also here, but when you actually look up the corresponding weights, you're going to need to subtract 1, I plus plus. And basically what we're trying to figure out is, okay, what is the answer to kxi, right? So that's what we're trying to figure out. And like we said, kxi, the key here is to remember that there's two cases. Either you take item I into the backpack, or you don't. Pretty easy. So again, in the case where you do take it, then kxi is going to be equal to the value of item I, because you took it, right? Plus k of x minus the weight of I, because now you have a smaller backpack to fill in, and you consider all I minus 1 items. So you already took item I, so you can't consider it again, so you consider the smaller set of I minus 1 up to I minus 1 items, and then you consider smaller backpacks because you already took it. The other case is where you don't take it, so then it's just k, how much can I, you don't take it, so you're looking at I minus 1 items, and you're still looking at the same x because you didn't take up any space. And the goal is, well, the maximum that I can fit here is just going to be the max of these two things, right? There you go. It's just going to be the max of those two things. So it's actually pretty easy. So you start with kx I. The very first thing you're going to do is you're just going to set that equal to kx I minus 1, right? So this is the case where I don't take the item. And then, the other thing to consider is this first case only exists if the item fits, right? So if the weight of item I is less than or equal to x, so if it fits in my backpack, then maybe I'll take it. So kxi is the maximum of kxi, or k x minus weight I, because I took it, I, and then the value of I, so the importance of I. So you add the importance because you took it, plus how much can I possibly fit into a now smaller backpack by weight I value, right? And you do that, that fills in your matrix, and then at the end, you just return k of w n. That is your answer. So again, this should probably work. You compile it. Again, hopefully that didn't take too long. You can fit a value of 6. That's actually the right answer. The last one's a little trickier, I'll say. You have a binary tree. This one's actually kind of tricky to implement. So I do point you in the markdown. I tell you, hey, something you can do here is you can head on over to lecture 28. and you can look at slide 8, I tell you, for the pseudocode. So we look at lecture 28. Oh, I put the wrong link, it looks like. Open up the slides, and we go look at this lecture, slide 8, I believe. So here, give you a pseudocode. This is actually a top-down implementation, which we haven't discussed that much. But a top-down implementation, you have to initialize global arrays A and B to be global. Okay, and this one's actually very tricky. This pseudocode is hiding a lot of complexity. So I encourage you to try it, but it's really tricky because you've got pointers, you've got a lot of if statements, you've got a lot of cases that you have to actually consider that the pseudocode does not consider. Okay, okay, so hopefully you guys are back. I'm going to jump into it now, or at least the implementation. So I hope that you guys tried it already. And the way I'm going to do it is I'm actually going to define a helper method to help me recursively keep my global arrays around. Okay, so I'm actually going to define a helper method called plumber revenue helper. That's going to take a binary tree pointer called houses. And actually my arrays A and B, in this case, I'm actually going to make them maps. Because I'm going to want to map, because again, like you have a tree, so it's a little hard for you to think about like, how do you number the elements in the tree, right? So again, like that's one of those things, again, like if you look at pseudocode, it's like, oh, like AU, where U is like the root of the tree, right? But like, how do you have an array that, of course, like you could keep like another tree, right? Like it's pretty complicated, but the easiest thing that you're going to see in practice is you just use a map. So we can use a map here, and you could have used a map for all the other ones. So we're going to use a map here, you know, an unordered map from binary tree pointers, okay? From binary tree pointers to integers. This is going to be my A, and it is also going to be a pointer because I'm going to pass it around and I'm going to modify it. I think I need to include unordered map. Unordered map. Oh, I misspelled include. I am going to pass it around. So it's going to be a pointer, actually, so that I can modify it without passing copies of it. Because I want it to be global in a way, but it's not actually going to be global. And then I'm going to have a similar map, which is the exact same type signature called B, which is going to keep the, you know, these are going to be my A and my B here, right? So one of them keeps the sum of the children weights, and the other one keeps the, you know, what is the maximum revenue that I can get from a tree rooted at U, right? So again, like the idea is that AU maximum, you know, maximum weight of tree rooted at U, and then BU is sum of children weights, sum of maximum weights of trees rooted at children of U. And the idea is that AU recursively is you have two cases. You either take AU itself, so you're going to have weight of U plus B of the left child and B of the right child, because you took U, so you can't take the left and the right, so you can only take their children. So you do B left, B right. Or AU, the other option, so that's one option. The other option is you don't take the root, in which case it's just A left plus A right, right? So you went to the left, you went to the right, and you take the max of these two options, right? Either the maximum weight is going to be you take the root, and then you don't take the children, but you maybe take the grandchildren, or you don't take the root, and then it's the maximum weight of like the two children, the left and the right, right? It's actually not super, like it's again, like it's pretty easy to describe the solution. It's a little tricky to implement, right? So you have to have these unordered maps to help you store the information. You have to create a helper method. And then all I'm going to do here is I'm just going to return plumber revenue helper of, I'm going to give it the houses, right? It's going to be my root. And I need to give it some storage. So I'm going to actually initialize my standard, my A and my B, and I'm going to pass them as pointers because, again, they're global. So they're going to be modified by all of the function calls. They're going to modify the same map. So that's A, B, but they're really just for storage. They're just helping me like save my answers in a sense, right? And what I do is like, pretty easy base cases. So if houses is null pointer, actually, let's not call this houses, let's call this root, right? So if my root is null pointer, then I can just, I suppose I can, I can just return 0. I don't even need to like save the answer anywhere. It's totally fine, right? And then what we want to do is we want to consider these two cases. So we have int first case, which is like take root. If we take the root, we start out at root. We have a minimum root value. Okay. If we don't take the root, so no root, we start at 0. Okay. So we know the root is not null. So I'm just trying to compute these two cases, this case here and this case here. So the first case I started with just WU because I take the value of the root. That's how heavy it is. And now I want to add B left, B right, right? But before I add B left and B right, I need to make sure that B left and B right have already been computed, which means I need to call myself recursively on my left and right children. Okay, so yeah, what I'm going to do is I'm going to call myself recursively on my left and right children. So you're going to call yourself plumber revenue helper on root left and plumber revenue helper on root right with A, B. So you pass in the same pointers. Okay. The idea is that this call is going to fill in my B left, B right, A left, A right. Okay. Because it's going to keep calling itself until it gets all the way to the bottom leaves. And then when it gets to the bottom leaves, it's going to fill those in. Okay. And we haven't finished yet, but at least this guarantees me that if I access these values, they should already be filled in. So now what I'm going to do is I'm going to say, well, if root left, so if I have a left child, right? So if root left is not null pointer, then when I take the root, there's two cases, right? I take the root. If I have a left child, then I want to add B left, right? So I'm going to look up B of root left. What was the sum of my children for the left child? Okay. If I'm not taking the root, then for the not root variable, I want to add a root left, right? And again, the idea here is because I called myself recursively, these values will already be filled in a way, okay? And we're actually going to use like at, I guess. We're going to look up at, and then at, which actually means that I think I need to do this. So I want to do A root equals 0 and B root equals 0. I want to set them. And again, the syntax is because they're pointers, you have to dereference it first, and then you go into it. So something like this. My base cases, they're both like, if I have no tree, then the answer is always 0. It's just 0, right? Otherwise, so I look it up. This is just so again, like this should never be. Actually, yeah, this should never be null pointer. So that's fine. So I just look it up. It should already be there. If it's not there, it's going to throw an exception. But I should have already saved that answer for that tree by the time I get here, right? Next, I'm going to check to see if I've got a right pointer, if I've got a right child. So again, so if this is not equal pointer, and it's basically the same thing, right? Except now I'm going to look at the right side, right? So in the case that I take the root, then I need to add how much are my grandchildren, how much are the children of the right side, right? So that's B at right. And then if I don't take the root, then I need to add how much can my right side give me, my right child, right? And then we want to save the answers. So now we actually have, we don't have the answer, but we can compute the answer, right? So now the actual answer is int, max weight is going to be the maximum of either taking the root or not taking the root. Okay, so we can actually say, okay, well, I'm going to save the answer. So A for root. So saving the answer into the map is going to be max weight. Okay, so again, this is where my leave saves its answer. So if I ever get to a leave, I call myself recursively, it's going to be null pointer. So these aren't going to do anything. They're just going to return 0, right? And I'm going to ignore that. And then yeah, these are just going to end up returning 0. I guess I could make this a void, to be honest. Anyway, whatever. I've got to return 0. It's going to do nothing. And then I'm going to have no children because I'm a leave. So then I'm going to take the max of 0, which is no root, and myself. So as long as I want to take myself, then I'll take that number, and I'll save that answer into A, right? So then when my parent calls me and he looks into the A map, he will find the answer, right? And then similarly into the B map for the root, this is actually just equal to the no root case, because it's the sum of the two children, which is exactly what the no root case was, right? It's like 0, and then we add the left and the right children. So this actually just equal to the no root. And then because I'm returning an integer, I actually have to return the max weight. So I might do this. There's probably better ways to write this, but that's basically it. And you'll see you get 7 and 9. And if you look at the answers, this is 9 and this is 7. So again, it's a little tricky it's tricky to implement. But I encourage you guys to try it. I give you the links to a lot of the code. We just walk through all the implementations ourselves right here. So I really encourage you to try it, and best of luck with this. And I'll see you guys on Friday for our lecture, and I'm probably going to do a homework party as well. So I hope you guys enjoy it. See you then.